Hello, in this video we will see an introduction to complexity analysis and a few examples of the same. We will see more examples in the coming videos. So when we say complexity of an algorithm, it could be either the space complexity or the time complexity of the algorithm. See, when we say space complexity, that is a space taken by the memory space taken by the program to run towards completion, and time complexity is the amount of time taken by the program to run to its completion. See, when we simply say complexity, it usually refers to time complexity. The reason being, the reason for not considering space that much is space is getting cheaper day by day. You know that the price for high memory devices are dropping day by day, isn't it? That is space. Price for space is getting cheaper day by day. And another thing is space can always be reused. The space taken by one program can be reused for another program once its execution terminates. So space complexity will not be considered. First reason is space is getting cheaper day by day, and the second reason is space can be reused. But in case of time, you know that time is getting costlier day by day, isn't it? The second thing is time can never be reused. So because of these two reasons, we all analyze time complexities of the algorithms. See again, when we say time taken by a program to run to its completion, we refer to the running time, not the compile time. Because a program which is compiled once can be run several times without any changes or modifications or recompilations, isn't it? So when we speak about time, it is actually the running time, not the compile time of the algorithm. Okay, again, what's the use of complexity analysis? See, for example, for the same application, for example, summarizing a particular text, assume that we have several algorithms. We have to analyze which algorithm is the best among them, isn't it? So one way to analyze the algorithm is by considering their time complexity. That is, which algorithm is giving you the perfect results faster. See, when we compare the algorithms, the output should be correct for all of them. So assuming that four different algorithms are summarizing a text correctly, when we analyze it, we will one measure of analyzing is which algorithm is giving you the solution faster. So that is the relevance of analyzing complexity of an algorithm. Okay. So one easiest way to find out the time complexity of an algorithm is finding out the frequency of various statements, frequency of execution of various statements in a program. I will show you an example. So we will see an example. For example, let the program be like this. Some variable sum is initialized to 0. Now for sum I is equal to 0, I less than n, I plus plus, sum is equal to sum plus a of n. Okay, let this be the program. Okay, as I told, one way to analyze or find out complexity of a program is to, or algorithm is to identify the frequency of, or summing up the frequency of various statements in a program. For example, or I am commenting it as program to sum of an array. Find the sum of an array. Okay. See the first. So what we have to do here is find out the frequency of execution of each and every statement in this program. So the first statement is the comment sum of an array. See, you know that comment is given just for the convenience of the user. The program has nothing to do with the comment. So frequency of the comment will be simply 0. So we will count the frequencies here. So frequency for counts will always be 0. Now the next statement is for comments will always be 0. Now the next statement is sum is equal to 0. As the statement is simply written, as it is not within any loops, the frequency of this particular statement will be 1, because it will be any statement that does not enclose within any loops will be executing exactly once, isn't it? So sum is c equal to 0 has the frequency 1. Now this thing, for I is equal to 0, I less than n, I plus plus, isn't it? See, for loops, this initialization part will not be considered, that won't be counted. See this body of for loop, how many times will it execute? See, in this case, when I is equal to 0, that will execute. For example, n is equal to 2. Assume that n is equal to 2. When I is equal to 0, it will execute this code once. When I is equal to 1, this will execute it once. When I is equal to 2, we are taking n as 2. So, 2 is not less than 2. So, this statement will be executed, but this code will not be executed, isn't it? So, this body will be executed when I is equal to 0 and I is equal to 1, and when I is equal to 2 also, this comes here and perform this control checking, isn't it? So, when I is equal to n is equal to 2, it executes 3 times. When I is equal to 0, I is equal to 1 and I is equal to 2, isn't it? So, when it is generalizing, if it is I equal to 0 to n, it will execute n plus 1 times. Okay. So now for brackets, opening brackets and closing brackets, the frequency count will be 0. So for these two statements, the frequency count is 0. And now for this statement, see, it will execute once. If n is equal to 2, it will execute first when I is equal to 0, then it will execute when I is equal to 1. When it is I is equal to 2, the control won't get inside the loop, you know that, isn't it? So when n is equal to 2, it will execute 2 times. That is when it is n, it will execute exactly n times. So this is the frequency of various statements in this program, and now we will count the sum of the frequencies. Now n 2n plus 2, isn't it? So 2n plus 2 is the frequency count of this program. Now when we say frequency, when we say complexity, we will take only this part of n, only the power of n. Here the terms containing highest power of n. Here the term with highest power of n is 2n, and we won't take the coefficients. So the complexity, for the complexity we will simply take n. Got me? That is, when we get a frequency count like this, we will take only the highest power term of n without any coefficient. So I have avoided the coefficient to power of n is 1, and this is the highest power term of n. And we say that the complexity of this algorithm is order of n. See, order of is an asymptotic notation which is used to denote complexity. We will see a very detailed video of asymptotic notation is very soon in the series. So for the time being, understand that we will take only the highest power term of n without any coefficients. So the complexity of this algorithm is order of n. We are avoiding all these constant terms because, see, when you are running in architectures with different configurations, that can affect the execution speed of your program, isn't it? Of your running your program in a quad-core system and running some other algorithm in a dual-core system, that can the quad-core system can speed up your program a little bit. So to avoid all such kind of speed differences because of the architecture, underlying architecture, we will eliminate all this constant terms. So we will take this only terms on highest power of n. See here, what is for I is equal to 0, I less than n, I plus plus, isn't it? That is, in this case, we are simply finding the sum of the array. So n is definitely the total number of elements in an array, isn't it? Or the number of elements that we are considering. So what does this mean? This complexity means that as the size of n increases, that is, size of input increases, the running time increases linearly. That is, if the size of the array is 100, the algorithm will take 100 units for execution. If the size of this array is 200, the algorithm will take 200 units nearly for time units for its execution. of the size of the array is 300, the algorithm will take 300 units of time to complete execution. What I mean to say is, see, if the complexity was n square, this is when it is order of n. This is the input size n. If it was order of n square, see, if the input size is 100, it is order of n square, isn't it? So it will be 10,000. If it is 200, that will be 4,000. If it is 300, that will be 90,000. 40,000, 90,000. So this is how the execution speed varies. So the inference that we can get from here is, see, assume that you and your friend have designed algorithms for a particular task. Your algorithm runs in order of n time. That is, when you counted the frequency of different statements in your program, you got order of n. While his friend calculated the frequency of execution of statements in his program, he got order of n square. That means, if the input size that I am giving you is 100, your program will complete its execution in 100 units of time. But your friend's program will take 10,000 units of time. If I am giving a program with the input size 200, your program will be executed in 200 units of time. But your friend's program will take 40,000 units of time for its execution. If I am giving you an input of size 300, your program will be executed within 300 units of time, but your friend's program will nearly take 90,000 units of time. So saying this, what it means is, a program, an algorithm which runs in order of n time is much better compared to another program for the same application which runs in order of n square times. So your program is better, much better than your friends. Okay. So this is what does it mean. So we will see more examples, a few very simple examples. In the next videos we will see complicated examples. So we will see a program for matrix addition. We will see the pseudocode, I should say. That is, for I is equal to 0, I less than some n, I plus plus. For j is equal to 0, j less than n, j plus plus, assuming that we are adding two array square arrays. Yeah. Now some c of ij is equal to a of ij plus b of ij. So you know that for processing a matrix which is a two-dimensional array, you need two for loops for processing the elements sequentially. Now c of ij is equal to a of ij plus b of ij. Initially I and j will be 0, so you will get the sum of elements at a of 0 0 and b of 0 0, the top left corner. Now j becomes 1, so you will get a of 0 1, b of 0 1. The sum will be in c of 0 1, second element from left on the first row, 0th row I should say. Okay, so now we will find out the frequency count for this algorithm, for this pseudocode. See, this loop is running from 0 to n. In the previous example, we have analyzed that some loop is running 0 to n times. The number of times this particular loop is executing is n plus 1 times, including the one final checking wherein the condition I less than n fails. You have to take that also into consideration. Okay. So the execution mean frequency is n plus 1 here. Now see, this for loop is nested inside this for loop, isn't it? So we know that. So if you are taking this bigger for loop, we have seen in the previous class that previous case that if the for loop is running n plus 1 times, the code within the for loop will run exactly n times. The reason is here this 1 is extra for this condition checking where this condition failed. When the condition fails, the control won't get inside, isn't it? So that case can be excluded because in that case the control couldn't reach inside this loop. So on every other situation, this code will be executed because this loop will be executed because this is nested inside this for loop. So n times under this influence of this loop, or to make, okay, under the influence of this loop, okay, whatever it is. Now see, this is a loop itself, isn't it? This is not a single statement. If it was a single statement, I could have stopped with this, but this is not a usual statement. This is again a looping statement. So this looping statement in itself will run 0 to n, that is n plus 1 times. So this into n plus 1. Okay. Now this statement is nested inside both these for loops, isn't it? So this for loop we have seen that will be running. See, this for this thing will be running n plus 1 times. Under this influence of this for loop, this will run n times. And under this influence of this main for loop, again it will run n times. So n into n will be the number of times this inner code runs. As it is not a loop, it can run only once on its own. Under the influence of this loop, it will run n times. Under the influence of this loop, it will run n times. So n into n. So now if you are adding up, you have n plus 1 plus n square plus n plus n into n square. So 2n square plus 2n plus 1. As I told you in the previous example, we will be taking only the highest power term of n without any coefficients. So that is definitely this n square. And just like we have done in the previous video, we will write it as order of n square, meaning that if there are 100 elements in the arrays, the execution time required will be in terms of 10,000 units. Okay. If there are 200 elements in both the arrays, the execution time will be 40,000 units. So it will be like that. So again, I am making a slight modification to this code so that you can understand it better. Assume that the one dimension, the matrix was not a square matrix. So the second dimension is n rows and m columns. Okay. So in this case, this loop will run 0 to n plus 1 times. Under this influence of this loop, this will be running n times, and as it is from 0 to m, this will be running m plus 1 times on its own, m plus 1 times. And under the influence of this loop, this code will be running n times, and under the influence of the main loop, it will run n times. And now you can calculate the total frequency count with the help of by summing up all this. Okay. Now we will see the example for matrix multiplication, which require 3 for loops. For I is equal to 0, I less than n, I plus plus. For j is equal to 0, j less than n, j plus plus. Now we are initializing some variable to 0, some k is equal to 0, so that the multiplication will run smoother. If you are confused about it, please to check the code for multiplication. For some k is equal to 0, k less than n, k plus plus. C of ij is equal to A of ik into B of I k plus C of I j. Sorry, C of I j is initially equal to 0, not k. Okay. So you can see 3 nested for loops here, one from this point to this point, another one from this point to this point, and a third one from this point to this point. Now we will find out the frequency count as we have done in the previous examples. So the frequency 0 to n, so n plus 1 times. This is from 0 to n, so n plus 1 times again on its own, but under the influence of this outer for loop, it can run n times. Now this code will run n times under the influence of this loop. It is again nested inside this for loop. So under the influence of this for loop, it can run n times again. Now this for loop, under the influence of this for loop, this will run n times. Under the influence of this for loop, it will run n times itself. And again, this is yet another for loop. This is not a single statement. This is a looping statement. So so on its own can run 0 to n, that is n plus 1 times. Now this code will run n times under the influence of this loop, n times under the influence of this loop, and n times under the influence of this loop. Now get the total frequency count, add all these frequency counts and take the highest power term of n without any coefficients, and you will get order of n cube. That is the highest power term of n without any coefficient. From this will be n cube. Okay. So that means if the arrays contain 100 elements, the multiplication will take 100 cube time to run to its completion. That is the inference here. See again, you might have understood that if there is a single for loop which is incrementing linearly, that is incrementing by 1, the final complexity that you got is order of n. That is the first example. And if there were two for loops which are linearly incrementing, that is simply by 1, the looping variable is simply incrementing by 1. The frequency that you, the complexity that you got is order of n square. If there are 3 for loops, the complexity that you got is order of n cube. That is, if this incrementation is linear incrementation, that is incrementing by 1, you will get, you can simply write this complexity down without doing much mathematics. That is, if 1 for loop, order of n, if 2 for loops, order of n square, and 3 nested for loops, order of n cube. Okay. We will see another program for I is equal to 0 to n. Print I for I is equal to 0 to n. Print L. See, the frequency count of the statement is n plus 1. The frequency count of this is simply n because it is running under the influence of this. The frequency count of this statement is n plus 1. The frequency count of this statement is n because it is running under the influence of this for loop. Now the total frequency count is 4n plus 2. And when we take the complexity, you will get that it is order of n. See, what I wanted to say is, you just do not have to count the total number of for loops. Even if there are 2 for loops, the frequency count can be simply order of n. If the for loops are nested only, the frequency will be order of n square. Okay. That is, if this for loop was nested inside this one, you could have got order of n square. If these for loops are separate, you will be getting something like this. So you have to be careful about that. You can't simply write order of n square just because there are two for loops in the program. Okay. Only nested for loops can be multiplied. Frequency counts can be multiplied. Only if the for loops are nested. Now we will see another program for I is equal to 0 to 100 prints A of I. Here we are printing all the elements in an array using the loop 0 to 100. So the frequency count for first statement is 101, you know that. The frequency count of this statement is 100, you know that. The total frequency count is 201. And I have advised you to take the highest power term of n without any coefficient. What will you take here? Here there are no terms of n, isn't it? See, if the program is like this means that the input size is independent of the total executions of this algorithm. That is, whatever be the size of input, the program is running exactly 100 times, isn't it? And I mean 201 times, isn't it? So that is there are no input size variable which is determining the execution time taken by the program. Whatever be the input size, the program will run exactly 201 times. This algorithm, isn't it? Otherwise, you have to change this 100 to some other value. Then that is some other algorithm, not this one anymore. That is, in this case, this algorithm is running exactly 201 times. If it is like that, we will say that this algorithm is having a constant complexity and we will write it as order of 1. Okay. To give you more examples, so we will see the complexity of popping an item from stack. You know that to pop an item from stack, what you have to do is you have to copy the value in stack of top to some variable and you have to decrement top, isn't it? This is how we pop an element of the stack. So see, this code will be executed just once, this code will be executed just once. That is, the complexity of the pop function is 1. That is, even if the stack contains 10,000 elements, pop will execute these two statements once each. So the total complexity is a constant number of executions are required, so the complexity is order of 1. Again for push, in case of push, you will increment top and you will push the value in some variable into stack of top. Again the same complexity, this will be running exactly once, this will be running exactly once, giving you the complexity, constant complexity, which can be denoted by order of 1. Okay. And all this complexity analysis makes sense when the input size is very large. We have defined this complexity analysis when the input size is very large. We will see that also in explanation for that also when we talk about asymptotic notations. So this is all in this video. We will see the examples of complexity analysis for bit more complex algorithms in the next video. Thank you.